In the past, this buoyancy stuff was a way to measure densities. And I think people still do this today. That's what's talked about in the feature problems. The feature problems kind of emphasize this density stuff. Like in number 91, Archimedes principle. Have you heard that before?
Yeah.
Archimedes principle. And it boils down to this. They used to measure densities like this. You have some kind of liquid here and some density, and they figure, well, these objects must be more dense. They're all sunk to the bottom. And these objects are less dense, and then if you have a floating object, then maybe it's equally as dense if it just floats there. And so we used to measure densities using things like specific gravity, etc. So this block here is more dense than ethanol, it's zinc. This block here is less dense than bromoform. Bromoform, look at that density, 2.890 grams per milliliter for a liquid. Is that high?
Very high.
That's very high. I mean, that's like aluminum, solid aluminum's less dense than this liquid. And so this liquid's really dense. But it turns out it's not the most dense liquid. Do you know what the most dense liquid is?
Is it
Mercury.
mercury?
Yeah. Mercury's density is like 13 to 14 grams per milliliter. So if you tried to swim in a pool of mercury, you couldn't. You wouldn't sink in mercury. You'd be floating on the top. In fact, you wouldn't even float. You'd just stand on the surface. That's fine. It's just way too dense. So you'd be like this in mercury. But this block, if it's floating by itself, then it's the same density as water. Underneath the surface. If it's floating like this, it's less dense. But if it's floating underneath the surface, it's the same density. But this one is a little bit heavier. Do you see that? And so we can figure out what the density is, because they attach a scale there. If the scale wasn't holding it up, it just sinks to the bottom. They just measured it. But we don't measure densities like that so much. So. So, what number did we leave off with?
87.
87?
Yeah.
Did we finish this one, or were we still working on it? Still working on it? All right, let's go ahead and finish this one. Okay, an empty 3 liter. So one thing I did I make a mistake with this? Yeah, so let's fix that. And so what we have is we have a bottle that's filled with ethanol. And what we want is we want the volume of ethanol. The volume of ethanol is going to be 3.00 liters, and we want the mass of ethanol. And so I just use that as the mass, but that's not the correct mass. Because I didn't subtract the mass of the bottle. And so 4.72 kilograms is the mass of ethanol plus the bottle. And so the actual mass of ethanol is only 3.02, or is it 2.02? 2.02 kilograms. In other words, the mass of the ethanol is equal to the mass of the bottle plus ethanol, which is 472 kilograms, minus the mass of the bottle itself, which is 1.70 kilograms, and that gives us 3.02 kilograms. And so to calculate the density, we need just to take the mass over the volume, but we want it in our units. And so after a while, you could do these conversions. 3.02 kilograms, we move the decimal 3 places over. That's going to be 3,020 grams of ethanol. And then 3 liters, this is going to equal 3,000 milliliters. Okay, I didn't really keep track of the sig figs here. And so I guess one way to keep track of the sig figs is to subscript it like this. And subscript this one like this, or just leave it. And so calculating the density, it's going to be 3,020 grams divided by 3.000 liters, milliliters, sorry, 3,000 milliliters. And so what does the density come out to?
1.006 repeating.
Okay, how many sig figs are we allowed?
3.
3. And so we'll just have to round this. Is this our final calculation? Let's see. No, this is not. How many grams of ethyl alcohol there in 250.0 milliliters of wine? So this isn't our final calculation, so we'll just hold on to it like this. All right, that's what we can get from the bottle part. What they want is, we have 250.0 milliliters of wine. This is the density of the wine we just calculated. And we have 11.5% ethyl alcohol. Ethyl alcohol is the same thing as ethanol. And so 11.5%, that means 11.5 out of 100. 11.5 what?
Grams ethanol.
Yeah, grams of ethanol per 100 grams of wine. This is a percent by mass. We could use any units here. So for example, we could use kilograms and 11.5 kilograms of ethanol per 100 kilograms of wine. We could use pounds, 11.5 pounds of ethanol per 100 grams, not 100 grams, 100 pounds of wine. And so we could use any mass unit or weight unit in a mass percent or weight percent. All right, so what we're going to do here is just do dimensional analysis. We'll just start off with 250.0 milliliters of wine. And then we need something that gets rid of milliliters or milliliters of wine. So is there something that gets rid of milliliters or milliliters of wine?
Density.
Yeah, the density here. And so for every 1 milliliter, we're going to have 1.00 sub 6. We're not allowed 3 sig figs. But since this isn't my final calculation, it's an intermediate calculation, we'll just use this. We could even use a bar if we want. But this would be grams of wine. Normally I'd want more sig figs, because if you look at how many milliliters I have, how many sig figs is that? 4 sig figs. And over here I'd like a minimum of 4 sig figs, preferably 1 extra or 2 extra. So I'd like 4 or at least 4, but preferably 5 sig figs here. That way I can minimize rounding error. But the data here doesn't support 5 sig figs, so we're kind of stuck with this. All right, so milliliters of wine cancel. That leaves us with grams of wine. And then I want something that gets rid of grams or grams of wine. And if I look over here, I have grams of wine. And so we can get rid of the grams of wine. 100 grams of wine for 11.5 grams of ethanol. And they're asking how many grams of ethyl alcohol are there, and so this is it. So how many grams? Calculate. $250 times 1.006 times 11.5 divided by 100. What do you end up with?
28.939.
28.9. Okay, we're going to be allowed how many sig figs? 3. So I'm going to write 28.94 subscript to 4 grams of ethanol. And here I can round off to 4, so this is going to be 28.9 grams of ethanol. So I think the reason that this was an advanced problem is because we had to figure out the density. The density wasn't given. If the density were given, it would just be a basic problem. But if you look at just the density alone, this would be a basic problem. And this dimensional analysis is just 2 steps, it would be a basic problem. But I guess you take these 2 basic problems and combine them, and you get an advanced problem. And that's what you find sometimes, you know. You find a lot of the advanced problems are just 1 extra step, or you take 1 extra branch, or you go off some way. Let's take a look at 88. The filament of an incandescent light bulb is made from tungsten metal. Density of 19.3 grams per cubic centimeter. Is tungsten very dense? Yeah, really dense. If you think about it, tungsten is about as dense as what? Gold. You know, although tungsten is not nearly as valuable as gold. In fact, I remember in geology we went to scheelite. Have you ever heard of scheelite? Scheelite's just south of Mammoth. It's in the Sierra Nevada. And there's a huge tungsten mine there, just north of Bishop. And so, anyway, didn't realize it was so dense. You know? And so this is why it's important to at least have some numbers, you know, reference numbers, you know, memorized, like lead. You know, lead is about 11. It's about half as dense as gold. Mercury. Mercury's really dense. Those are all pretty dense. So tungsten's surprisingly dense. That has been drawn into a very thin wire. Okay, so in this problem we have tungsten wire. Do you know the symbol for tungsten? W. Good. So we just have a thin wire filament. This is tungsten solid. The density, tungsten, 19.3 grams per cubic centimeter. The diameter of the wire is difficult to measure directly. It's pretty thin. So it is sometimes estimated by measuring the mass of a fixed length of wire. If a 0.200 meter length of tungsten wire, okay, so we're going to have a 0.200 meter length. So if we know the length, and we know the mass of this wire, it weighs 42.9 milligrams. It's pretty small. So it's got to be a very thin diameter here. And so from the length, we can also figure out the volume, because the length times the area will give us the volume. When I look at this problem, it looks familiar. Then what is the diameter of the wire? Express here. The diameter of the wire, well, we know that the area of a circle is equal to pi r squared. And so if we can figure out the radius, then we could figure out the diameter. And so this is basically the same kind of problem we did earlier. We have the volume. I mean, we don't have the volume, but we could figure out the volume. We could figure out the volume by taking the mass, go from milligrams to grams of tungsten, grams of tungsten to cubic centimeters of tungsten. Cubic centimeters of tungsten is equal to this volume, area times length, and then just solve for the area, and then solve for r, and then calculate the diameter. And so this looks just like the, what was that, the copper wire problem, and also the triangular bar problem. And so the 3 problems in the advanced section that are very similar to one another. And so I'm not going to finish this one, but it's very similar to what we've already done. All right, let's take a look at number 89. Number 89, blood alcohol content BAC is sometimes reported in weight volume percent. And when it is, a BAC of 0.10% corresponds to 0.10 grams of ethyl alcohol per 100 milliliters of blood. So one way to differentiate this is a BAC here, and it's 0.10%. And it's a weight volume, so it's a W over V or M over V percentage. And so weight to volume or mass to volume. Chemists use weight and mass interchangeably. And so we don't make the distinction. And the reason we don't is because, you know, the force of gravity doesn't really change much on the surface of the Earth. Whereas if you went to the moon, then for sure we need to know the difference between weight and mass. Again, masses don't change, but weights do change because weights depend on the force of gravity. The force of gravity on the moon is 1/6 that of the Earth. Okay, the other thing is this percentage. You know, these aren't as common. M over V percentages. You see this like in biology. For example, blood. Blood, they have something called isotonic saline solution. Have you heard of that? Isotonic saline. Isotonic saline is a solution of salt that has the same concentration as the blood. You know, blood has different things dissolved in it. And so they want the same total concentration. And that's 0.9 M over V percent, 0.9 salt. So that means 0.9 grams of salt per 100 milliliters of blood. In this case, it's 0.10% W over V, which they tell us what it means. This means 0.10 grams, so that's the weight of the mass of ethanol or ethyl alcohol per 100 milliliters. This would be the volume of blood. So that's what that goes there. In many jurisdictions, a person is considered legally intoxicated if his or her BAC is 0.10%. How about in California? Do you know what it is? I think this is DMV. 0.8? Wow, 0.8 is pretty high. Pretty high. That's almost, I think that would be in the alcohol poisoning region. It's actually going to be 0.08, yeah. That's California, so California is always more strict. So 0.08 would be, but we're going to use 0.10. Suppose that a 68 kilogram person, so we have a 68 kilogram person, has a total blood volume of 5.4 liters of blood. So we could make a ratio here, or we could leave it as is. And breaks down the alcohol at a rate of 10.0 grams per hour. So 10.0 grams of ethanol are broken down or metabolized. Let's just say broken down per hour. People metabolize alcohol at different rates, so there's a little asterisk here. So let's read the note. The rate at which ethyl alcohol is broken down varies dramatically from person to person. The value given here for the rate is a realistic, but not necessarily accurate value. And so somebody might have this rate, but another person might not. How many 145 milliliter glasses of wine? So it's 145 milliliters per glass of wine. Consumed over 3 hours will produce a BAC of 0.10% in the 68 kilogram person. So 3 hours. And then we have a 68 kilogram person. Assume that the wine has a density of 1.01 grams per milliliter. So that means we have 1.01 grams of wine per milliliter of wine. And is 11.5% ethyl alcohol by mass. So we're going to have 11.5 over 100. 11.5 what?
Grams ethanol.
Grams of ethyl alcohol or ethanol, ETOH for short, per 100 grams of what?
Wine.
Wine. Okay, so let's try dimensional analysis for this. And so I'd like to start off with something extensive. Property is my given. What should I use?
I think it was 5.4 liters of blood.
Yeah, if it's a 68 kilogram person, then it's got to be 5.4 liters of blood. So we could start off with that. Or we could start off with 68 kilograms, cancel out 68 kilograms and get 5.4 liters. And so we'll just do that. 5.4 liters of blood. You know, there are other ways of doing it. But we want to get rid of liters or liters of blood. Do we have any relationship with liters of blood? Yeah, we do. We could get rid of liters of blood and go to 68 kilograms. Should we do that? No, because that would kind of be going in a circle. Because once we get 68 kilograms, then the only way we can go is to 5.4 liters of blood. Or I guess we could go to grams or pounds a person, but that's not going to help us. And so let's get rid of liters and go to milliliters. Okay, now I have milliliters of blood. Is there something that gets rid of milliliters of blood?
You can go to grams.
Yeah. If I have milliliters of blood, I can go to grams of what? Ethanol. So let's do that. 0.10 grams of ethanol per 100 milliliters of blood. So milliliters of blood cancel, that gives me grams of ethanol. And so what I want to do is I want to get rid of grams or grams of ethanol. Do I have something that gets rid of grams of ethanol? Yeah, I have this, but if I were to use this, I'd just go back to where I started. Right? So I need something different.
You have the ethanol percent in the wine.
Oh yeah, we have 11.5 grams. 11.5 grams of ethanol per 100 grams of wine. So now I have grams of wine. Is there something that gets rid of grams of wine or grams?
Kilograms.
I could go to kilograms of wine,
You have the wine density.
but we have the wine density here. So if I go 1.01 grams of wine, that's per milliliter. So I could just say 1 milliliter of wine per 1.01 grams of wine. And so the grams of wine cancel, and that leaves me with milliliters of wine. Is there something that gets rid of milliliters of wine or milliliters? And yeah, there is. We have the wine glass. The wine glass holds 145 milliliters. And so one glass holds 145 milliliters. And what this is going to tell us is going to tell us how many glasses of wine we can consume to get a 0.10 percent blood alcohol level. So let's see how many glasses that comes out to. 5.4 times 1,000 times 0.1 divided by 100 times 100 divided by 11.5 divided by 1.01 divided by 145. We had 0.32063 glasses. Not even one glass. It's about 1/3 of a glass, a little less. Does that sound about right? No, that doesn't sound right, because when you have your driver's license, they give you a little sheet saying how many drinks you can have, right? And what was it? It's like one drink in 2 hours or something like that? Or one drink in an hour, isn't it? And so this seems awfully low, doesn't it? Only 1/3 of a glass, and you already can be arrested in California, because California is 0.08. And so if this is 0.08, that's like 2% less. And so you shouldn't drink maybe 1/4 of a glass of wine, and then you're okay. You're going to be arrested if you drive. But what about all this other data here? You know, they said how many 145 milliliter glasses of wine consumed over 3 hours will produce a BAC of 0.10% in the 68 kilogram person. So am I using the 3 hours here? No. Should I have added some more conversion factors? It's a little bit tricky. This is kind of a tough problem. There are different ways to handle this, but what should I do with the 3 hours here?
We need to use it for where they break down the ethyl alcohol
Yeah.
at 10 grams per hour.
Right, we got to see how much ethyl alcohol is broken down in 3 hours. So if I have 3 hours of time, how much ethyl alcohol will be metabolized in that time period? And so I have 3 hours, and then I need to get rid of hours. So what gets rid of hours here? 10 grams per hour. And so 10 grams of ethanol will be metabolized in 1 hour. Well, 10 grams of ethanol is how many glasses of wine? And so if I have 10 grams of ethanol, then where do I go next? I need to get rid of grams of ethanol or grams?
We can use the 11.5%.
So should I use this? This will take me to blood.
Would you use
No.
the second to last? The other one next to it?
This one?
The next to it?
This one?
Yeah.
Okay. Would it cancel out this one here? If I do 1.01 grams of wine, will the wine cancel out with the ethanol? No, because wine is a mixture of ethanol and other stuff. Uh-huh. Okay. Yeah. This one, the 11.5 grams of ethanol per 100 grams of wine. And so this is pure ethanol, not wine. And so the grams of ethanol cancel, and that leaves me with grams of wine. You know, out of every 100 grams of wine, you're only consuming 11.5 grams of ethanol, and the remainder, 88.5 grams, would be water and all the other stuff that's mixed in with the wine. Okay, then where?
From grams to milliliters?
Yeah, grams to milliliters. We're going to use the density, 1 milliliter of wine, or 1.01 grams of wine. Okay, and then where?
Glass.
Yeah. And so 1 glass of wine contains 145 milliliters. And so this is going to tell us how much ethanol is metabolized in 3 hours, 30 grams of ethanol. And those 30 grams are going to be from how many glasses of wine? So there's going to be 3 times 10 times 100 divided by 11.5 divided by 1.01 divided by 145. Oops, I made a mistake. Did somebody calculate it?
Yeah, I got 1.7812875.
1.7821?
2875.
2875.
And then there was a 1 between the 8 and the 2. Yeah.
Okay, thanks. Is that what other people got?
Yeah.
How many sig figs are we allowed here? It's hard to say. You know, it depends on how precise this is. And this could be 1 sig fig, and it depends on how exact you want. So we could say in exactly 3 hours, approximately how many glasses or how many grams of ethanol are consumed, and what does that equal in terms of glasses of wine. So 1 or 2 sig figs. Because we probably don't have to write this many digits. But what you can do is this. After consuming 0.3 glasses of wine, you're already legally intoxicated. But that's not factoring in the metabolism of the ethanol. And so if you were to drink 1.78 glasses of wine and then wait 3 hours, what would your blood alcohol content be?
0.
0. And so we need, at time 0, we need to consume this, 1.78 glasses, and then by 3 hours it should go to 0. And then on hour 3, how much more wine could you drink? Because if we're down to 0, then we're well below the legal limit, and to bring it back up to the legal limit in some states, we could drink another 0.3. And so there's a bit of timing here. We need to consume all this wine. Well, we need to have, you know, we need to have excess ethanol in there so it continually metabolizes. And so there's a bit of timing here, you know, to drink this all at the beginning and then kind of wait. And then you could have a little more at the end. If we don't have this at the end, what's going to happen? Well, it's still going to continue to metabolize. Although if we're already saturated here at 3 hours, and then just add on time. And so altogether, this is how much wine we could have. It's going to be, combining these, it will be 2 point, what? Do 2.1, or give me some more digits.
2.10191.
Okay, we'll just go with that, glasses. And so to round this to 2 sig figs, we'd call it 2.1 glasses total. Or to round it to 1 sig fig, we'd just have 2 glasses of wine in a 3-hour period. So if we had 2 glasses of wine over a 3-hour period, we should be safe. But it depends. If you have 2 glasses of wine at the end of your 3-hour period, you're not going to be safe, right? All right, so this is a complicated problem because we had to do 2 different calculations. There are other ways that people did this. Some people will calculate the amount of alcohol. We'll do it that way. All right, that's chapter 1. The reason I like to look at all the questions is then I can feel a little bit more comfortable going into tests. You know, you've seen at least all the hard problems in the homework, and therefore, this goes the same for the basic problems in the homework. Or, if you do all those problems, and all the advanced problems here, and then all the other problems, the feature problems, And then they have a little quiz here at the end. So this is the feature problem. Then they have the self-assessment quiz. Okay. And so then you'll see a lot of variation in problems. And then it gives you a little boost of confidence, if you're comfortable with these problems. What I do is, since I look at the answers sometimes and then just jot down some notes. When I told you I review my lecture notes, like daily. I also review the homework. So I do the homework in the notebook and then just go back through the problems so I don't forget, how to do those. So by the time the exam comes, if there's a question on the exam that's anything similar to the homework or anything similar to what was presented in the lecture, I thought that was a give me problem, an easy problem to answer. If you could do those quickly, because the exams at UCLA are timed, you have 50 minutes and you can't go over 50 minutes, except for the final. The final exams at UCLA are 3 hours. But if you go through these quickly, then you have a lot more time to spend on the problems that don't quite look like the homework, or the problems that aren't quite direct from the lecture. And so you have more time to do the advanced problems, the step above the advanced level. But not everybody has time to do this. This is a nice thing to do. To be able to do. And I've spent a lot of time on it already. So I want to move on to the next chapter. And the next chapter deals with atoms and the atomic theory. This is similar to like Chem Floor. Atomic theory part 1, it doesn't quite tell us, how we can predict the properties. And so, like in Chem 4, we break up atomic theory into 2 parts. 1, just looking at the atom, its basic composition and structure. And 2, we look at the electrons. We look at the orbitals and that type of stuff. The orbitals and that type of stuff is atomic theory part 2 or quantum theory. And that's going to be in a later chapter. And so we aren't really going to talk about orbitals at all in this chapter. And so a lot of this kind of review and the basic outline of the sections is very similar to the Chem 4 text. So in an effort to save time, we're just going to condense all these sections kind of into one. Early chemical discoveries in the atomic theory, electrons and other discoveries in atomic physics, the nuclear atom, chemical elements, atomic mass, introduction to the periodic table, the concept of the mole and the Avogadro constant or Avogadro's number, using the mole concept in calculations. And that's pretty much it. So when you think of atoms, how do you visualize the atom? What's in the center of the atom? The nucleus. And the nucleus is tiny, right? We have a tiny nucleus. And that tiny nucleus contains what?
Protons.
Yeah, the protons and the neutrons. Protons we abbreviate P or P plus, and neutrons N or N0. The plus is the charge, and the 0 is the charge on the neutron, which is neutral, no charge. And so we have this tiny nucleus. Maybe I'll make it a little bit bigger than that dot there. Okay, where are the electrons? Yeah, the electrons, are they orbiting around the nucleus?
It's like a field. Like they're always moving.
Yeah, they're always moving. In a predictable path? No. It's kind of unpredictable. You guys remember the Heisenberg uncertainty principle? Heisenberg? What was Heisenberg's uncertainty principle? Actually?
can either predict its position or something else, but not both.
The direction of its spin.
The spin is part of the quantum, the fourth quantum number, but the electron is, okay, what we do is we kind of pinpoint the energy of the electron, and therefore its position is uncertain. So we describe the position of the electron in terms of probability. That's pretty much the Heisenberg. There's going to be a compromise, but for chemists, we take one side of the compromise. That is, we want to know what the energy of the electron is. But if you know the energy, then you don't exactly know what the position is. But the electron is said to be in empty space, right? The electrons occupy the empty space around the nucleus. And what is empty space? Empty space has no what in there. Like empty, if it's perfectly empty space, do you know what we call that?
Vacuum.
A perfect vacuum, right? A vacuum just means you suck all the matter out of the space, and if there's no matter in there, then it's empty space or vacuum. But there could be something in there. You know what's in empty space, a perfect vacuum? What's still there?
Orbitals?
The orbitals are the potential positions that could be there, you know, and so the orbitals, yeah, they could be there, but there's something else that's always present.
Is it like electromagnetic?
Yeah, like electromagnetic fields. Like we could have a perfect vacuum here, but you know there's the Earth's magnetic field, and the Earth's magnetic field would be penetrating into the empty space. And so we could have electric fields. We could have gravitational fields. You know, there's some supernova in a far distant part of the universe. And after that supernova explosion, there was ripples in the gravitational field. Did you hear about that? And these ripples in the gravitational field were traveling. And it just so happened they were passing by Earth. Last year or the year before? Just recently, in the last few years. And so before the ripples in the gravitational field arrived, some physicists set up some instruments to measure the ripples in the gravitational field. And, you know, they actually measured it when that little ripple in the gravitational field passed by. But there's another thing that occupies this empty space, and that's called the Higgs field. Have you heard of the Higgs field before? And the Higgs field, they actually did a simulation of this, and I saw the video of the simulation, but I was looking for it and I couldn't find it. I gotta do this because sometimes, you know, I pull up something and it just comes up. Other times, it doesn't. Oh, here it is. I was looking for this earlier and it didn't come up, but now I see it here. Is there any audio? There's no audio, so I'm going to skip this. There it is. That. Okay, so this is the simulation here. This is based on theory. And so this is not somebody's imagination, but from the theoretical calculations, this is what they're saying. And so empty space is not really empty. There's fields in there. But we'll come back to this later because there's something else we need to know. Is there a wall, like a fence around the atom? No. There's no fence. And so what that does is, we don't know. We can't pinpoint the electron. So how big is the atom? Well, it depends on where the electron is. If the electron's closer here, it's smaller. If the electron's further out, it's bigger, right? But, what we do is we look at the probability, and there's going to be a probability, orbit or a probability cloud. The probability cloud. And then what we do is we stick probes in here, or we see how these atoms interact with other atoms. So there's going to be something called the atomic radius or the atomic diameter. For orbitals, we call this a 90% probability boundary, or maybe even a 95% probability boundary. We have 90% probability of finding it within this boundary, or 10% probability of finding it outside this boundary, depending on what we set the boundary at. And this is going to give us some size indication. This is an s orbital. Other things we just look at, probing this. Although this should be in the center there, nucleus. All right. As far as size goes, the size of the nucleus is extremely small. But how big are atoms roughly? So we set up this boundary here and then estimate the size of the atoms. Do you know about how big an atom is?
1 to 6 angstrom.
1 to 6 angstroms, or in terms of picometers, it would be 1 to 6 angstroms in diameter, or in terms of picometers, it would be
600.
100 to 600 picometers. That's about how big an atom is. How big is the nucleus?
Maybe like a couple picometers.
A couple of picometers is too big.
Really?
The nucleus would be about 1/10,000 of the size of the atom. And so 1/10,000th of the diameter, roughly. So 10,000 times smaller. And so if we make this 10,000 here, then it would be 1. All right. What do we know about the protons and neutrons? Well, tell me more about this. What is this model called, or of the atom?
The Bohr model.
Not the Bohr model. The Bohr model had the orbits, like planetary orbits. That was the Bohr model. The Bohr model relied on this picture of the atom, but the Bohr model is incorrect. Because the electrons don't orbit. The electrons are just somewhere around the nucleus here. This is called the nuclear atom model. There was another model. Do you recall the name of the other model? The other model was called the plum pudding model. But actually, let's go back to the protons and neutrons. Protons, neutrons, and electrons are called subatomic particles. They're smaller particles in the atom, and these are the subatomic particles that make up the atom. And so what do we know about the protons and neutrons? Well, we know how much they weigh. So the proton mass is 1.6726 times 10 to the minus 24 grams. So the proton weighs 1.6726 times 10 to the minus 24 grams. The neutron's mass is about the same, 1.6749 times 10 to the minus 24 grams. And so the neutron weighs slightly more than the proton, not by much, just slightly more. In physics, they use kilograms instead. And so if we use kilograms, rather than 10 to the minus 24, this would be 10 to the minus 27. This would be 10 to the minus 27 kilograms. And the electron is not nearly as massive. The electron weighs 9.1094 times 10 to the minus 28 grams. Or I had to memorize this in physics, but I memorized it in kilograms. 9.1094 times 10 to the minus 31 kilograms of the electron. And so grams is maybe not the most useful unit for this. Do you know what the metric prefix is for 10 to the minus 24? No, I don't either. I don't, but I do know the metric prefix for 10 to the minus 12. What's the metric prefix for 10 to the minus 12? Pico. So 10 to the minus 24 is 10 to the minus 12 times 10 to the minus 12, right? And so this would be 1.6749 picograms. So we could just call it picogram. But it turns out there is a metric prefix for 10 to the minus 24. I just don't know what it is. And so I guess we could call it picograms. But even if we called it picograms, it's not so convenient. What's a more convenient unit to measure these particles? Milligrams? Yeah, milligrams, kilograms, grams. They're all kind of awkward.
Moles. Moles.
Moles? Moles, yeah, we could use that, but moles tells us the number of units, but not necessarily the mass or the weight. Is there another mass unit that we could use? I mean, would pounds be more convenient? No. Pounds wouldn't. Ounces? Yeah, grains is still, it's going to be a huge number. And so it turns out there's a much more convenient unit, and that is the atomic mass unit. And so this would be equivalent to 1.0073 atomic mass units, or U. This one would be 1.0087 atomic mass unit. And so these are both very close to 1 atomic mass unit. The electron is going to be 0.00054858 U. And so if we measure these small particles in U, it's a bit more convenient than in grams or kilograms. You know, the SI unit, what's the SI unit of mass? The kilogram, and there is a kilogram standard, a primary standard for the kilogram. Do you know what it is? It's locked up in some vault in France. It's a chunk of platinum palladium alloy, and that chunk of metal locked up in a vault in France weighs exactly 1 kilogram by definition. So they just got this chunk. They say this is going to be exactly 1 kilogram. And then we could use that to calibrate everything else. And so do they have a 1 U chunk of platinum palladium metal locked up in a vault in France?
I don't think so.
No. And so what weighs exactly 1 U? What are we going to use as our primary standard for the atomic mass unit? You know, we have to have something so that we can calibrate our balances to make sure they're reading correctly. And so how are we going to calibrate this for the U? What are we going to use?
Maybe something for 12U.
Yeah, there is something for 12U. In fact, there's nothing. You know, there's nothing that weighs exactly 1U. Nothing. And that's because it's defined differently. There is something that weighs exactly 12U. What is that? Yeah, carbon, but not just any carbon. It's carbon 12. And so 12U is defined as the mass of a carbon 12 atom. A carbon 12 atom, you know, sometimes we call this a nuclide. And so a nuclide of carbon 12 weighs exactly 12U. And so this is what we use to calibrate our balance. But we don't use balances. Can you weigh a single atom? No, not on a balance. How do we weigh single atoms? We have to use a special instrument. Do you know what that special instrument is?
A mass spectrometer.
A mass spectrometer. Good. The mass spectrometer allows us to weigh single atoms. Now, how can you weigh single atoms using a mass spectrometer? The way we do that is we get a sample of carbon. And so to get a sample of carbon, what are the forms you can buy carbon in? Well, we can buy it in graphite. I just bought some graphite. It was pretty cheap. We got some 99.99% graphite. Or we could buy diamonds. You know, diamonds are pure carbon too. And diamonds are going to be too expensive, so we'll just use graphite. And so graphite's going to consist of a whole bunch of carbon 12 atoms. And in order to weigh one of these, what we do is we use a laser. You use a laser and you hit it on the surface here. And what it does is it takes the solid carbon 12 atom and vaporizes it into the gas. And so now we have a single gaseous carbon 12 atom. Can we weigh it? Yeah, in fact, if you continue hitting this, we'll get more and more gaseous carbon 12 atoms, and then we can weigh those. Now, how does a mass spectrometer work? So let's take a look at the mass spectrometer. So we put our sample in there, and then it says heater vaporizes the sample. We're going to need more than a heater. I mean, if you try to heat up graphite or if you try to heat up diamond, it's not going to vaporize it into gas. And so we need some more power here. And that's why we're using the laser. Here, laser hits this, vaporizes it. Okay, once we vaporize the sample, that is the carbon 12 atoms, then we need to have those move through our mass spectrometer, but they aren't going to move. And so the next step in this is we're going to charge them by using an electron beam source or electron gun. And so, have you heard of a CRT? Cathode ray tube? You know, think of an electron beam. Can you think of an electron beam? You've seen a beam of electrons before. Who was it? Was it Benjamin Franklin? Who flew the kite? Thomas Edison? Was it Benjamin Franklin who flew the kite in the lightning storm? Yeah, so lightning, a bolt of lightning is a beam of electrons, but it's quite jagged. It's quite jagged because it's hitting air particles or air molecules. So it hits that and then does this jagged path. And so what we do in a CRT, as a cathode ray tube, is we suck out a lot of the gas and create a vacuum in there, so that when the electron beam travels, it doesn't collide with a whole bunch of stuff and turn into a jagged lightning-like beam. And so you get a nice consistent beam across there. And so how do we generate this lightning bolt? The way we generate the lightning bolt is just have a voltage. You know, it's the same thing that happens with lightning. You know, there's a, let's say, positive charge on Earth or negative charge, and then, you know, things travel. So what we do is we create a positive charge and a negative charge, or actually negative charge here, positive charge here. And if the voltage gets high enough, and the other processes that happen, then we get a beam of electrons. So we have this beam of electrons. And you can do things with that beam of electrons. So for example, all the old monitors used to use these, all the old televisions used to use CRT, cathode ray tubes. Cathode ray tubes keep back here, and they have this beam of electrons. It goes out and hits the monitor. Fortunately, we still aren't using these. But we still use cathode ray tubes as a electron beam source. So there's a cathode ray tube here, generate a little beam of electrons, like a controlled lightning, and it's not going to be as energetic. We don't need quite the voltage for this. And this beam of electrons hits. When a beam of electrons hits a carbon-12, an electron can get stuck on it, creating an anion, a negatively charged ion. Or if the beam is strong enough, it can knock electrons off, creating positively charged ions. So what it does is it creates ions. Once we create ions, then we put plates here. So if the electron gets stuck there, we put positive plates here. And this Coulomb's law says unlike charges attract. So negative charges attract the positive, positive charges attract the negative. And so we put a charge here on the plates here by just using power source, a battery or something. And then that accelerates the carbon-12 atoms through, and then they collate these into slits here. And so the carbon-12 atoms are accelerated, and then they hit a magnet. And when charged particles hit a magnetic field, it deflects them. And so the lighter ones are more heavily deflected. The heavier ones are less heavily deflected. And so the carbon-12s will get deflected and hit the detector. Where the carbon-12 hits the detector, then we calibrate the detector, saying that where the carbon-12 hits, that mass is exactly 12 AMU. And so this would be called like a primary standard. Have you heard the word primary standard before? What is a primary standard? What's it used for? A standard. What are standards typically used for? Well, the kilogram standard in France is used to calibrate balances, to make sure that balances are reading 1 kilogram. A primary standard is, do you make that kilogram standard out of steel, or do you make that kilogram standard out of platinum and palladium? You make it out of platinum and palladium versus steel. Why? Yes, steel is going to oxidize. It's not stable. And so in the previous homework problem, they didn't call that steel the primary standard because the primary standard has to meet a higher bar. That is, it has to be stable. And so this is why platinum palladium is so unreactive. It's stable. And so we use that as primary standard. The same thing here. Graphite, this is pretty stable stuff. Yeah, carbon could oxidize, but I'm not going to hold my breath. It's hard to burn. Have you ever tried to burn graphite? Like take the pencil lead and put it in the flame. Is it going to catch on fire? No. The wood will catch on fire of your pencil if you have a wood pencil, but not that graphite. In fact, it's going to take extreme temperatures. The same thing with diamond. Yeah, carbon should combust. And so diamonds, in theory, you should be able to burn those in a fire. But do you think they're going to burn? No. And so primary standard, this would serve as a good primary standard. And so we feed these carbon-12 into the mass spectrometer, and then what we get is something called a mass spectrum. This is all done on the computer. The mass spectrum is going to show us the mass, and then on the y-axis is something called the intensity, or the percent. We're going to use computers. And then we look at where the carbon-12 atoms hit. Okay, one hits here, another hits here, another hits here, and this peak just grows. And so all the carbon-12 atoms are hitting here, and therefore this mass must be exactly 12 U. It's carbon-12. Do you know what carbon-12 is made out of? How many protons, neutrons, and electrons? Yeah. Carbon-12 has 6 protons. In fact, This is called the nuclear symbol. The nuclear symbol has two numbers usually associated with it. Most people don't write this number, 6. Do you know what this number is called? This number is called Z. And it's called the this number up here is the mass number. The mass number is given the symbol A. Is that it? This is the mass number. Interestingly, the mass number is not equal to the mass. It's approximately equal to the mass, but not equal to the mass, except for carbon. Carbon is the only atom where the mass number is equal to the mass. Every other atom in the periodic table, the mass number and the mass don't. They're just slightly off. They don't agree. What is the mass number? It's not a mass, it's a number. And it's the number of what plus the number of what? Yeah, it's the number of protons plus the number of neutrons. Since a proton and a neutron weigh about 1, and the electron is a lot lighter. How much lighter is an electron compared to a proton or neutron?
1/10,000.
Yeah. Well, 1/10,000th is a little bit too high. You know what it is? It's about 1 over 1850. You can just take that and divide it. And so it's about 1/1850, or about 2,000 times lighter. We just round it to 1 sig fig. So it's about 2,000 times lighter than the proton and the neutron. So most of the mass is in the protons and neutrons. And therefore, if you have 3 protons, that's going to be about 3U. If you have 3 neutrons, it's going to be about 3U. And altogether, you're going to have 6U plus the electron's mass. But the electron's not so significant. And so this is why the mass number is approximately equal to the mass, but not exactly equal. This is another thing we have to factor too. Okay, what's Z called?
Atomic number.
Z is called the atomic number. And most people don't write Z. Why? How did you know it was 6?
First number of times.
Well, not exactly that. What is it?
I said because you have the same number of protons and neutrons.
In each what?
Would it not be 6? Would we not have 6 protons and 6 neutrons?
Not always.
Is it because it's just carbon?
Yeah, it's because it's carbon. Carbon is defined as having 6 protons. If we had 7 protons, is it still carbon? No. If we had 7 protons, what element am I looking at? Nitrogen. And so the Z is off the periodic table. It's a red number at the top of the box. And so we don't need to write that. If it's carbon, Z's got to be 6. And so it's a bit redundant. So a lot of people leave it off, like me here. But the atomic number is the number of protons, and the element is defined by the number of protons, not by the number of neutrons, because the number of neutrons can actually change. So for example, do you know that not all carbon atoms have 6 neutrons? You know, there's another carbon atom present in graphite and diamond that has 7 neutrons. It's called carbon-13. And so when I vaporize this, I'm going to get carbon-12 and carbon-13 coming off. Are there any others?
Yeah.
Yeah, there are. Have you heard of carbon-14? But the situation with carbon-14 is carbon-14 is radioactive. Radioactive atoms are unstable. And the reason they're unstable is because the nucleus is unstable. You know, there are all kinds of things that help in terms of stability of the nucleus. And so carbon-14 is what we call not natural. You know, it's radioactive. And so when we look at a piece of graphite or we look at a piece of diamond, what we look for are the naturally occurring isotopes. Isotopes are atoms of the same element but different number of neutrons. With a mass spectrometer, we can figure out how many isotopes there are in nature. So if I take a piece of graphite like this, I'm going to get another peak here. The next peak will be carbon-13. And it depends, you know, if it's a 50-50 mix of carbon-12 and carbon-13, then the peaks are going to be the same height. You know, half the atoms will be carbon-12, the other half are carbon-13. But it turns out it's not a 50-50 mix. Do you know which one's more common? Carbon-12 or carbon-13? It turns out carbon-12 is more common. And are there any other isotopes for carbon? It turns out there are no other naturally occurring isotopes because we only get 2 peaks. And so this one's going to be carbon-13, but the carbon-13 peak is weak compared to the carbon-12 peak. Based on the peak heights, we can determine that the percent natural abundance, have you heard of the percent natural abundance? The percent natural abundance is this. 98.89% of the carbon atoms will be carbon-12, and 1.11% of the carbon atoms will be carbon-13. And so over here, we're going to see over here that 98.89% of all the carbon atoms will strike here, and only 1.11% of the carbon atoms will strike here. And so we can get this from the peak heights. This is going to be, if I say this is 100%, then 98.89% will be this, and 1.11% will be that. And so from the mass spectrometer, we get the percent natural abundance. And we get the mass, because if this mass spectrometer is calibrated with our standard, this is a parameter standard carbon-12, then we can use some physics to determine how much the carbon-13 weighs. The carbon-13 doesn't weigh exactly 13. The carbon-13 weighs 13.00335 U. And so the carbon-13 is going to hit at 13.00335 U. And so mass spectrometer, we get 2 pieces of information. We get the mass of the nuclid, that is the mass of this atom of this particular isotope, and we get the percent natural abundances. Actually 3 pieces of information, if I want to split it like this. 3 pieces of information. The number of isotopes equals the number of peaks. Only 2 peaks here, therefore 2 naturally occurring isotopes. The percent natural abundance of each isotope and the mass of each isotope. So 3 important pieces of information that comes from the mass spectrometer. Now, those are the naturally occurring isotopes, but what about carbon-14? Carbon-14 is a radioactive isotope, so if I wanted to know all the isotopes of carbon, these are all the isotopes of carbon. And so I'd look at a table of nuclids or a table of isotopes. These are radioactive and non-radioactive isotopes because carbon-12 and carbon-13 are not radioactive. I can tell by this, the decay mode, that is radioactive decay mode, and the half-life. These both are stable, so these are naturally occurring. But when I look at carbon-14, it's radioactive. The decay mode is it emits beta radiation. Beta radiation is particle radiation. We'll probably talk about that later. And there's something called the half-life. The half-life is 5,730 years. A half-life. That means it takes 5,730 years for half the population to decay. And when carbon-14 decays, it gets converted into other things. But take a look at some of these others. These are all synthetic isotopes. you know, made in the laboratory. A lot of these are just made in the laboratory. Or carbon. A lot of these are very unstable. So for example, if I look at carbon 20, its half-life is 14 milliseconds. So it doesn't live for very long. Carbon 21, it's so unstable they didn't collect any data. Carbon 22, the same thing. These are so unstable they didn't collect any data. This one's not so bad. Well, carbon 14 is not so bad. Carbon 15 is not so bad. And so even though they say that these are the two naturally occurring isotopes, carbon 14 does occur naturally. You know, there's some processes that occur in the atmosphere that creates it. And so this is why it's used for radioactive dating. Okay, what else do I need to say? All right, the next thing I need to say is this. If I know what carbon 12 is made out of, it's made out of 6 protons, 6 neutrons, and 6 electrons, and I know how much the protons and neutrons and electrons weigh, can't I figure out the mass without having to weigh it? You know, in other words, if I wanted the mass of carbon 12, then can I just sum up the masses of the subatomic particles?
Does it depend on whether you,
Add the electrons as well, because it says like the sum or the weight of electrons are negligible. Is that, it doesn't create a big increase in.
Well, a lot of people ignore the weight of the electrons because they don't weigh that much, but you know, for accuracy, just include them. It's not so hard to include it. Yeah, we should be able to do it. So let me ask you this. Another way of determining mass, because a mass spectrometer is expensive, and then you need a vacuum, and you got to suck everything out, and then you got to get a laser to do this if you want carbon 12. You can calibrate it with other isotopes. Once you know what carbon 13 is, or once you know what some of the other isotopes are, then you can calibrate it. You don't have to use carbon 12. You can use whatever is convenient. But it's still a hassle. And so rather than having to do this experiment to weigh this, why don't we just add it up? And so if I want the mass of carbon 13, it's just 6 protons, so 6 times this, plus 7 neutrons, 7 times this, plus 6 electrons, 6 times this, just sum them up. Does that work?
No.
No, it doesn't work. And so the sum of the mass of the subatomic particles is not equal to the mass. Of the nuclid. The nuclid is a single atom of that isotope. Why?
I forgot what it's called, but some of the mass is like converted into energy to like keep it together.
Yeah.
So it's like a little less.
Right. It's called the mass defect.
Yeah.
You should know the mass defect. The mass defect just says that some of the mass of the nucleus is converted into energy to hold the nucleus together. And that amount is not fixed. It's not like, okay, 5% of the mass is always converted into energy to hold the nucleus together. It varies because some nuclei are very strongly held together and stable. Those nuclei that are strongly held together and stable we call stable isotopes. But some nuclei are weakly held together and barely are hanging on there. The nuclei want to break apart. And those unstable nuclei are what we call radioactive. The nuclei are unstable for one reason or another. And so the amount of energy, or the amount of mass that's converted into energy, varies. And so it's going to depend on this. So E, what we call the nuclear binding energy, the energy that's required to bind the nucleus together, is equal to mass times speed of light squared. And so E is equal to, now the mass we say delta M times C squared. So sum of the mass of the nucleus is converted to energy. Why do we need this? This is E equals mc squared, which is a very famous equation. Well, we need to do this is because we need to know about the forces of nature. What are what are the forces of nature that you can think of? Gravity.
Magnetism?
Electromagnetism.
Yeah, electromagnetism, electrical, and magnetic. Well, these are often combined because they're related one another. And
Weak and strong.
weak and strong what?
Forces.
Yeah, the nuclear forces. The nuclear are broken down into the weak and the strong. The weak, that's this is a misnomer for chemists. And so what's the most important force in chemistry? The electrical force is the most important in chemistry. Chemists, they deal with light attracts like charges repel. Actually, like charges repel, unlike charges attract. So positive negative is good, positive isn't, negative isn't. And so for chemists, electrical forces are the main. Gravity, no. And a nuclear, no, because we don't like to work with radioactive. Unless you're a nuclear chemist. For nuclear chemists, what do you think is most important? Or if you're a nuclear chemist or a nuclear physicist, the most important will be the weak force. And the most important is the weak force because it's the weak force that does what? Nuclear chemist, physicist. The nuclear chemists are interested in the weak force because this is what holds the nucleus together. And so if you have 6 protons in the nucleus, in this tiny nucleus, if there's 6 positive charges, Coulomb's law says that those 6 positive charges should repel each other. Are we out of time? Yeah, sorry. You can stop me if I go over time. But we'll continue this next time.